Still considering our non-unity feedback systems, now we're looking at sort of that second case where we have different units for our input and output. So our input and output units are not the same. And so in this case, we can't find our steady state error. So we can't find steady state error. But as we mentioned before, what we are going to find is the steady state error of our actuating signal. So of actuating signal. And ultimately what we're going to do is we're going to sort of go back to basics and do something similar as to what we did when we first found the equation for our unity feedback system. So here's our block diagram, and again, now we're assuming we have different units for our input and output, and that's possible because we have this feedback block H as opposed to our output simply being fed to our input. So what we can say then is we can say that this actuating signal, E sub A, is equal to R minus H times C. And so I'm simplifying and leaving off the parentheses S just to sort of reduce some clutter and confusion. And so of course we can say, well, really our C is just EA times G. So we can say EA is equal to R minus H times EA times G. And so we can solve this for EA, and what we get is that our EA is equal to R divided by 1 plus H times G. And so again, this is a similar form as what we saw previously when we were considering our unity feedback systems. And so just like with our unity feedback systems, we said we don't really want to take the inverse Laplace transform because that can get messy. So instead what we're going to do is we're going to use our final value theorem. And so with our final value theorem, we can then say the actuating signal steady state error, so EA as t goes to infinity, is equal to the limit as s goes to 0 of s times our EA, and our EA is given by this here. So we have the limit as s goes to 0 of s times r divided by 1 plus h times g. And so something to keep in mind is that this equation is only for this configuration shown above. So only for above configuration. So if we have a block diagram that is not in that same configuration, we have a couple options. One is we can use block diagram algebra until we reduce it to something that looks like this. The second option is we can leave the system how it is and we can redo analysis similar to this to get a different expression for the steady state error in our actuating signal.